Alright, so this is the demonstration of a simulator for the custom computer architecture. Uh, so we have two different emulators. We have this low-level emulator, and then we have this what is a higher level emulator of this 4-bit architecture. So let's start off with the low-level emulator. This one simulates the hardware at a very low level. So it's actually simulating what each circuit would be doing in the computer were it to be made out of hardware. And each circuit is represented as a class, and they update on every clock cycle. So let's load a program that this could run. So it runs assembly code. So let's just find something appropriate for what to run. So let's find the determinant of a matrix. So what this code does is, this computer architecture is a 4-bit architecture. So this means that it can really only address up to 16 lines of code at once. But we can get around this by whenever halt is activated, it will clear those lines and then load the next 16 lines. So these lines right here are going to input all the values. Then right here we are going to do A times D. If you recall, the determinant of the matrix is A times D minus B times C. So these lines right here is just a multiplication loop. We are implementing multiplication using a sequence of additions. And then we have to do B times C. It's done in these lines of code. So B times C. So what we're doing is we're doing A times D and we're storing it in RAM. And then we are doing B times C, and we are storing it in RAM as well. And then what we do here is we do subtraction. We do A times D minus B times C, and then we output it. And then we halt, and it stops running. So that's how the code works. So let's just provide it with an input. So we are going to be doing a matrix 1, 2, 3, 4. So A is 1, B is 2, C is 3, D is 4. So let's start off with 1. Let's actually start the clock speed at 1. So we're doing input, and then stow. Alright, so now we can change it to B. And then we have to be careful with the clock cycles for this one, just because of how this one works. So input, and then stow. So stop the clock. 1, 2, 3. So as you recall, it stored them in RAM. So input 1, 2, 3, and 4. So what's doing is it's loading the value, putting in the accumulator, and then storing it in RAM. So now we're going to input 4, store it in the accumulator, and it should go right here in RAM. And so these are the values. Alright, so now it's going to go to the next part of the code, so we can actually increase the clock speed. So let's do 20 hertz because this kind of takes a while. So we're stepping through all the instructions, and right now we're just going through the multiplications. So this is a loop. It's going, these branch instructions are just telling it what to do. And any minute now it should be done. Alright, so it just finished, it halts, and it stopped. The clock is still going, but the code is not executing anymore. So we could just stop it right here. Alright, so let's check this. In a matrix 1, 2, 3, 4, the determinant is A times D minus B times C. So that means it's 1 times 4 minus 2 times 3. So that means that it's 4 minus 6. 4 minus 6 is negative 2. So the determinant of this matrix should be negative 2. And if you look at the output register right here, that's exactly what it says. The determinant of this matrix is negative 2. Alright, that's fine and all, but now let's look at the other simulation. This is a high-level simulation, and this one is a bit different. So while they both simulate the same architecture, this one does it on a higher level. It more so focuses on executing the assembly code than it does simulating the interactions of the physical hardware itself. Uh, and on this one, it is connected to a couple of peripherals. First off being this keypad, and this keypad basically just writes a digit to the input register. So this is connected directly to the input register. So that means rather than typing directly to the input register, you could use the keypad. More interestingly, you also have a simulated LCD. This is a simulation of a 16 by 2 LCD display, like what we had on a microcontroller. So this one is actually simulating the commands that would be required to be sent to the LCD, so it can clear and basically print characters one at a time. Those characters are represented by ASCII code, which is 8 bits. So that leaves us with the problem. This is a 4-bit emulator, and the output register is 4 bits. So we are using a simulated shift register, and that connects to the LCD. So we have this LCD shift register. The shift register, you can input data on it in a serial fashion using the output register. So in a very complicated way, the output register, what writes to the shift register, which writes to the LCD, sends the commands so we can get a display. Let's demonstrate this with another program. So in theory, this program is much simpler than the last, but it is quite a bit longer. It is 1,200 lines of code, and as we mentioned before, it can only load 16 lines at once. So you're loading effectively this, and then as soon as you reach halt, you load the next 16 lines. That's what the halt command does. Think of it best as a physical analogy of a stack of punch cards. So we are loading the first 16 elements, which is like what's written on the first punch card, and then we're loading the next card. And we cannot address stuff that from over here because it can only address 16 lines. But using this non-addressable memory, we can address an arbitrary, or we can't address it, but we can run an arbitrary amount of code, and they interact with each other by loading stuff to and from RAM. Also each 16 lines is an element in a linked list in the code. So let's start it off at 1 kilohertz. And we don't have to be careful about the clock frequency here because this does have a input polling loop. So you can see it's input and it's just waiting for the input. So let's multiply two numbers. So the two numbers we want to multiply are 2 and 4. So it's going to ask for another input. Alright, so it stopped again. It wants another input. So let's give it 4. So now it's going to do the output. What is 2 times 4? 2 times 4 is 8. So it's just the output. And 2 times 4 is 8, and that is found in the output register right here. So the one thing to note is that both the output register is connected to the LCD shift register at all times. But this 8 doesn't interfere with what's on the shift register because you have to do a lot of things to enable the shift register to actually store a bit, and then that has to go to the LCD. So effectively we can write whatever output we want on the output register, and it's fine. Alright, so that is the demonstration of the simulation. Now we could look into the code a bit more. So you could see that the code has some major components to it. Obviously you have main window.cpp. What happens here in this Qt code is that we're essentially on action triggered. We are loading the file. So this gives us the file IO so we could load the assembly code. And it loads it into the ROM. The ROM is a linked list. So this is the ROM array, and then we're okay, and then we could store that in a linked list. So we're doing append ROM right here. There is actually some residual code here for an 8-bit emulator, but that was not implemented in this version of the code. So also we have to switch between the different parts of the window. So like the 8-bit or the not the 8-bit emulator, the 4-bit emulator is split into a low level and high level emulator. Those are each on different pages, and how we navigate pages is on here as well. Alright, so let's go to the high level emulator. And what this does is it just decodes the instruction using a switch case statement, and then it does the appropriate action. So if it has to multiply something, if it has to load a value in RAM, if it has to do an input, it does this. So all this is happening right here. And then we are doing some other stuff. Here's the instruction to append the ROM to the linked list, which is quite important. Yeah, and then we also have the clock. The high level and low level emulator have different clocks. Also for the high level emulator, you could increment the clock by pressing a button, and then you could increment one clock cycle at a time, or you could do it automatically using a timer. The low level emulator is a bit more interesting. It still has the same clocks, but there's a lot more going on here. It's very complicated. Here is basically a bunch of comments saying what's happening. It is simulating it's basically simulating the chips of the physical hardware. There's a lot to say here. It's all listed in the comments of the code. So if you're interested in that, go read the code. Yeah, so this is actually what's running. So each piece of hardware has an update function. So, and then we have get value functions. So yeah, that's pretty much what's going on. Here's something for the decoder. It's just to show it. This is not really part of the hardware. It's just to show what's being displayed, or what instruction is being executed. And this is the Alu encoder. What this does is the ALU has its own instructions which it wants. So what this does is it takes whatever's in the instruction decoder and it produces something that the ALU would like, and then it just returns an integer. This would also be a physical piece of hardware, but since it's just a combinational logic, there's no need for it to be an object, as it doesn't have any persistent values. It's basically just a function, and that's what it is represented as. So really most of what's going on is this stuff right here. So we're just setting the registers, and it would be really hard to go over what's doing here, but we're basically just updating the accumulator, and it's going pretty much how it's all wired. So this is basically, think of it as the wiring of the computer. It's basically everything is taking in what it needs to take in. So for each of the physical pieces of hardware, there's a class for that. We have several different classes. We have the ALU. This is the ALU. Once again, this could probably have been implemented just as a function, but since all the R1s were classes, I just put this as a class, whatever. The counter right here just simulates a 4-bit counter. You could do several things with it. You could clear it, clock it, increment it, and then you could load a value from the input. So this is how you are able to do branching. Is if you select to load, it will load the input, and that will be the count output, and then you could get the count by this get count function. We also have this reset count function. This is used for programming purposes. You could do it using the update function. So this doesn't simulate the hardware really, but it is just for the ease of programming. Then you have this decoder right here. Once again, this probably could have been a function, but it's not. So basically we have Boolean values for every single instruction with this computer can execute. So not, or, and, load, branch, branch if 0, add, subtract, stow. So all these are our Boolean values. Well, you could say, oh, you could have represented all this just as an integer, but for how this is meant to be doing, it's not really supposed to be the most efficient code or whatever. It's supposed to simulate the hardware, and this is more accurate to the simulation, as these would all be like separate lines. So these are like, well, basically wires if you think of them like that. The LCD, this is not used in the low-level simulation, but it is a low-level simulation of the LCD, though it is only used in the high-level emulator. That's a bit complicated, but yeah, this is just a simulation of a 16:2 LCD display. We have our inputs to it. We have register select. What this does is this determines whether or not the LCD is expecting a character input or a instruction. So the LCD has several instructions. The most important one is to clear the LCD. So if we're inputting an instruction, we'll want to clear the LCD or do something else with it. But if we're inputting a character, we want what's read from the data to be a character rather than an instruction. And the data is only read when enable is pulsed. And then we have the get LCD value. The LCD, what does it do? It outputs a string. So here's the output, it's a Q string. Then we have the RAM. This is simulating what's a 64-bit RAM chip. This chip is used for the RAM and the ROM, but what it does is it has 16 4-bit addresses. So that's what it does, and we could do that just as an integer array. Technically, this does allow us to use numbers larger than 4 bits, because this computer's idea of what an integer is different from what the simulated architecture has an idea of what an integer is, but nonetheless, you still only have 16 values to store. Then we have S, which is basically the output, and then we have write enable, memory enable. So what these allow us to do is to read or write to the memory, or we could just disable it entirely and take it out of the system. That's useful because it's connected to a bus. So if we don't want it writing through the bus, we could just disable it entirely. And then we have A, that's the address. D is the data input, which it will read only when the RAM is set to write. Then we have get RAM val. It just get the current output of the RAM. And then we have get RAM value at. Once again, this is not a hardware specific thing, but rather than having to address the RAM, we could get the value at a specific address. So we're basically looking inside of the RAM chip. This is not something you will be able to do with the hardware, but as you've seen with the Level Emulator, this allows us to see what's in every RAM address at any point in time. So this is important for that. So then we have registers. A register is just basically just an integer that stores a value, and then we could clock it, and on the rising edge of every clock cycle, the register will update, and it will output whatever is in the register using the get reg value at, and then there's an update. Notice how all of these have an update function, because we are updating it every clock cycle, and then when we want to get the value, we get the value, and we put that to whatever input that has to go. Like, for example, the ALU register has to input its value to, the ALU register has to output its value to the ALU. So the ALU would just reference this function of the ALU register. Then we have the shift register. Once again, this is used on the high level emulator for the LCD, but it is a low level simulation of a shift register. So the shift register has several different things that it could do. It has SR clock. This inputs values into the shift register. You have the R clock. This will update the outputs of the shift register. So you load values into the shift register one value at a time, and then you output them by pulsing this. And then you have the data input. This is just a serial input. And then you have clear. You could clear the shelf register, which is something that makes writing characters to the LCD a lot easier because you can just clear everything and start from scratch. And then you have the SR latch. This has to do with the clock. So the clock cycle is you have a counter and then you have a sub counter. So the sub counter basically steps through the program, or it steps through the execution of each instruction, whereas the main counter, what it does is it addresses the ROM. So it basically the program counter gets whatever instruction has to be executed, and while you are on that instruction, the sub counter, which is another type of counter, steps through the execution of that instruction. Basically, it's like, okay, so let's say we want to add the add instruction, and that is like the accumulator is equal to the accumulator plus the RAM address value. So what the sub instruction counter does is it goes to each it like loads the ALU register, then it pulses that, then it pulses the accumulator register, and then it does it one step at a time. In order to do that, this SR latch is needed because basically whenever the instruction counter, well, whenever the program counter is pulsed, it flips the SR latch, and the sub instruction counter counts up, and once it reaches 4, it will flip it back so that the program counter can move on to the next instruction. This could be seen within the schematic of the architecture. So now we can go back to the low-level simulator and actually see what's being done right here. So yeah, so here's all what's going on here. So everything the computer does is in here. So this is the auto clock. So every clock cycle it will increment. First thing we have to do is, well, first we're showing what the clock cycle is, and the clock cycle is either 1 or 0. So it's like 1 0 1 0. That's the clock. And now we update the sub counter. Again, it takes in the clock. It also has the latch. The latch is important to have the sub counter be enabled or not. And then we're saying we're not going to load anything, and if we do load something, it's going to go to 0. So that's like for the conditional jump instructions, or just the jump instructions, the sub counter always goes to 0 by default. Alright, so then we are getting the output of the sub counter, and we are updating the latch. So the latch, again, it's important for the program counter to know when to cycle up. Notice how the sub counter has the clock, has the system clock, whereas the program counter is clocked by the latch. So that's quite important right here. And then whether or not we jump is based off of B and BZ. So are we going to jump? Well, that depends. If it's unconditional jump, then we will jump. If it is conditional jump and the condition is met, then we will jump as well. And where we jump to is always going to be the whatever's on the data ROM. So then the instruction ROM, we're going to update that. So we are going to address the ROM which holds the program instructions. So this is kind of based more off of what would be a Harvard architecture than a von Neumann architecture, because it has a separate memory for its for the program and for the variables, basically. So we are addressing the program memory based off of what the program counter says to do. And then we're updating the UI, and now we're doing the same thing with the data ROM. So the data ROM and the instruction ROM are both 4-bit memories, but together they are basically combined together, so we can have 4 bits of instruction and 4 bits of data. So let's say like the add instruction has 4 bits that says this is the add instruction, and then another 4 bits that says which address in memory we are going to add, just for an example. And then the instruction decoder is going to decode the instruction and give us all of the appropriate things to execute. So if it is halt, we are going to load the next elements in the linked list, and if it doesn't exist, then we'll just stop. So if the instruction is halt, we will load the ROM. And as I mentioned, this is kind of simulating a stack of punch cards. And then we're going to reset the count of the program counter and the sub counter upon halt. So we're going to stop it, and then else, if there's no next element in the linked list, if basically we are done with the program, it will stop. And then we're also showing the decoder values, and that just to show it on the user interface. So also right here is if we're doing add, subtract, load, and or the B is going to be the system RAM get val. So basically these instructions want a RAM address, so we are going to give them the RAM address, and that is the RAM address in the system RAM. The instruction load value, however, it wants something from the data ROM, so it will give it that to be, and then the input is going to write B to whatever's in the input register. The B is basically think of it as a bus. So this bus, it could either be something from the RAM, something from the ROM, or the input register. So now we're going to update the ALU. As I mentioned, the ALU has its own instructions with it, which it wants. But yeah, we have the input A, input B. So it's going to be the accumulator, and the B is going to be this bus, and then we have S, M, and CN, and this is just going to be the encoder value. So the ALU encoder is just going to say whatever these things need to be, or whatever these things are set to execute a particular instruction on the ALU. Think of it like that. And then we have to write the accumulator ALU register, and yeah, so that just kind of goes based off of whether we're getting input, get add, get subtract. So this is just like whatever instruction is appropriate. And then also we write the accumulator, and the ALU register is always written first, because sometimes we need a persistent value from the accumulator or from the ALU, because the ALU has no memory. So what the ALU register does is it gives the ALU memory. So we could say accumulator equals accumulator plus something. So we have a working memory with the ALU register. And then the accumulator register will execute. And notice how the placement in the code doesn't really matter, because this only goes whenever the sub counter is 3. So this goes when it's 0. So the ALU register will be set when it is 0, and then the accumulator goes later. So if we're executing the add instruction, it is the accumulator is equal to the accumulator plus a value. So basically this stores the accumulator plus a value, and now we are safe to change the accumulator. And that's done right here. And then we show its value, and then we write the ALU register. And then we also have the output register is written if the instruction is get out. So if we are writing, if the instruction is to write the output register, then we do that. Again, this is done on the first instruction of the subcounter. So this will happen. It'll be the second thing to happen. So the ALU register goes first, and then the output register also goes first if it is called. And then we are also writing the RAM. This also happens at the same time. So pretty much think of it as the timings of it is the RAM, the output register, and the ALU register go at the same time, whereas the accumulator goes later because sometimes it needs a persistent value. And then this is just showing what's in the RAM, and we're going through the instructions right here. And then we're encoding values for the ALU. We also have all of these CPP files for each of the things. So yeah, so this ALU, again, it's based off of a physical piece of hardware, and it just implements a switch case statement. The counter counts up, and also we have this stuff right here so that it only goes on the rising edge of a clock. So that way, because that's what the hardware would do. The LCD, again, it can take an instruction, or it could write a character, and that's just done here. The RAM, yeah, it takes in the values, and if it is set to write, then it does that. If not, it'll just read it. The register will display the value that it is appropriate. The shift register will shift a value through an integer, and then it will return the value get shift register out. So just going through this. And the SR latch is simulating an SR latch. So if it sets, then it sets. If it resets, then it resets. It's quite simple. So that's a demonstration of pretty much what's going on. So I hope you found this video informative, and thank you for watching.